All right, greetings, welcome. I want to take a look at exercise 7.1 from chapter 7, in which we're going to calculate pressure drop using the Colebrook equation to determine the friction factor. So let's read through this. So air under normal conditions flows through a 4 millimeter diameter pipe with an average velocity of 60 meters per second. We wish to determine the pressure drop in a 0.2 meter section of the pipe. For air under normal conditions, the density and viscosity can be taken to be 1.23 kilograms per meter cubed and 1.79 times 10 to the negative 5 Newton seconds per meter squared. The pressure drop may be computed as this, where L is the length of the pipe and D is the diameter of the pipe, Rho is the density of the fluid, and V is the fluid velocity, and F is the friction factor. So before we look further, all right, just looking at equation 7.11, the goal here is to calculate delta P. On the right hand side, we're given L and D, the length of my pipe and my diameter. We're given the density and we're given the velocity. So I'm trying to solve for delta P, okay, but on the right hand side, I don't know F, right? So once I have F, then I can use 7.11 to explicitly solve for delta P. All right, so now about F. For this problem, we have turbulent flow. The turbulent portion of the Moody chart is represented by the Colebrook equation, which is given as such, where epsilon's the pipe roughness and Re's the Reynolds number, defined as this. Okay, and then we're given two different values of the relative roughness to consider. So now knowing this, right, looking at 7.12, right, we're given a roughness, right, and then we know the diameter, so we know the relative roughness. And in terms of Reynolds number, we could compute the Reynolds number because we have rho v d and mu. So we know this, right? We know this. So 7.12 is a single equation with a single unknown, which I can use that to solve for F. And since this is a single equation with a single unknown, right, and it's nonlinear, in the context of chapter 7, right, I know I can solve this using fzero. And so looking at this, I'm going to have to solve my problem sequentially, in which I'll use fzero to solve 7.12 for F. And then once I have the value of F, I can use 7.11 to directly solve for delta P. Okay, cool. Let's do it. So I'm going to jump over to MATLAB. Okay, and I'm going to create a new function. And so this could be function res, I'll call dpcalc. Okay, and then seeing that I'm going to need to evaluate my pressure drop for two different cases of the relative roughness, I'm going to make my roughness, okay, which is in millimeters, an input. Okay, and so setting up my documentation, okay, this is going to be a function to compute pressure drop in millimeters or in kPa for a given given roughness in millimeters for our specific problem. All right, so as if this were a transport exam or problem, I could make a density, viscosity, diameter, length. I could make all of those inputs, but I'm not for now, and we could always change it up. Okay, I'm going to specify all those within my function as parameters, and then I'll just have as an input this relative roughness, which I may want to look at the effect of. Okay, cool. And so I'm going to start by going through and listing out my parameters. So my diameter is 4 millimeters. So this is diameter in millimeters. And so if I were to convert that to meters, okay, I'm going to convert it to meters, okay, just because here it's relative roughness, epsilon over d. So if they're both in millimeters, right, it's dimensionless and it cancels. But in my Reynolds number, I'm going to put everything in SI units so I can ensure that the units cancel out. So I'm going to go ahead and I'm going to convert this to meters as well. I'm going to do that by dividing by 1,000. Okay. Then next, we have the velocity. It's 60 meters per second. And so I'm just going to say my velocity is 60. Okay. and this is my velocity in meters per second. And what I'm going to do here is I'm actually going to get rid of this underscore m, right, and just use the underscore to kind of note the units if we're not in SI units. So I have my velocity, my length of my pipe. So length is equal to 0.2. That's my length of pipe in meters. So I have length. Now I have density. So rho was equal to 1.23, and that's density in kilograms per meter cubed. And my viscosity, which is in 1.79 e to the negative 5, and that's Newton seconds per meter squared. Newton meters per second squared. Okay. All right, great. And so what I'm going to do next is I'm going to go ahead and I'm going to calculate my relative roughness, since I know I'll need that here, and my Reynolds number. And so I'm going to start by computing relative roughness. Okay. And let me call that, say, ED. My relative roughness is going to be my roughness in millimeters, and then I'll use my diameter in millimeters, right, so that it's dimensionless. It's my roughness in millimeters divided by my diameter in millimeters. Then I'll compute the Reynolds number. So my Reynolds number is rho times V times D divided by mu, where all are in SI units. Okay. All right, so I have all my parameters. I have ED and Reynolds. All right, and we said when we were going through this is the first step is I'm going to need to numerically solve my Colebrook equation, equation 7.12 for F. Okay. Now I could do this two ways. So one, I could write a separate function, and that function is going to have an input of F, what I'm trying to solve for. But then I'll also need to pass to it my relative roughness and Reynolds number, which are two parameters that are needed, right, to solve that equation. Now if I do that, fzero requires an error function with a single input and a single output, so I would need to use an anonymous function to pass that additional information to it, relative roughness and Reynolds. What I'm going to do is, since this is just a single expression, and this should be easy enough to type on one line, is I'm just going to write my whole error function as an anonymous function. And I'm going to do that because when I define my anonymous function, right, that anonymous function exists within my current functions workspace, and so it has knowledge of my relative roughness and Reynolds number, so I can just use them within the function, and I don't need to define or pass anything to it. And so I'm going to go that route. And then last comment is when I think about writing an error function, remember this is going to be a function that's going to have a single input, f, right, what I'm trying to solve for, and then my function should evaluate to 0 when I find the value of f that I'm looking for. And so I need to set this up. I'll bring this over to the right hand side so that my expression evaluates to 0 when I find the f that satisfies my equation. Okay. So I'm going to create my error function. Okay, and so let me call this Colebrook error. And so this is going to have an input of f, and then it's going to return back, or it's going to evaluate, so 1 divided by square root of f plus 2 times log base 10. And it's going to be my relative roughness, ED, divided by 3.7 plus 2.51 divided by, I'll put that denominator in parentheses because it's Reynolds times the square root of f. Cool. So there's my Colebrook error. Okay, and now I'm going to need to solve this, right? And so what I'm going to do is I'm going to plot the results here and kind of get an idea of where my zero might happen. Okay, and I know my values of f, right? They're going to have to be positive and greater than 0. All right, if I put a value of 0 in here, I'm going to get 1 divided by 0, right? That's an issue. And negative, I'm going to start to get imaginary numbers since it's square root of f. And so I'm just going to start. And ideally, when I use fplot, I should vectorize this. But MATLAB will just complain a little bit, but it'll still work. And so I'm just going to plot my error function, and I'm going to look from, say, 0.01 to 1. And let me just see what I get. Okay, so I'll save this as dpcalc. Okay, actually, so before I run it, this is underlined, which means I didn't use it. And looking, that's because I spelled rough wrong over here. R-O-U-G-H. Okay, so now that's good. So I'm going to call dpcalc. And then the first case we had was 0.26. Okay, so I get a little message that my function is not vectorized. Okay, and it looks like I got lucky. So if I look from 0.01 to 1, all right, we're positive. All right, then we go negative, and we cross 0 somewhere over here about 0.1. Okay, that's cool. If I were to try for the second case, which is 0.0015, let's see what happens. 0015. Okay, looks like that's also suitable range. We're positive. All right, then we're negative. I cross 0. Now it's just a smaller value, right? So it's less than 0.1. Okay, cool. So what I think I'm going to do though in terms of the range is to make this general, because we might want to look at other friction factors as well. Looks like as the relative roughness increases, right, my friction factor is going to increase, and then as my relative roughness decreases, right, my friction factor is going to decrease. And so what I'm going to do is, instead of giving a range, right, I said we should always give a range if possible. I'm actually just going to give an initial guess of 0.1. Just this way, in general, right, if I have a relative roughness that's just too small, some outside that range, or too high, some outside that range, right, if I give it a decent initial guess, it should hopefully still be able to find brackets which it can use to solve. Okay, but it also looks like my error function works. All right, so now solving for f. Okay, I'm going to call this, my friction factor, and it's going to be equal to, I'll call f0, Colebrook error, and I'll give it an initial guess of 0.1. Okay, and now that I have my friction factor, okay, let me make this larger. Once I have my friction factor, now we can solve for dp, and that's going to be in pascals, because I'll just have everything in SI units. And so that's this equation. So dp is equal to my friction factor times L over D, my L divided by D, times 0.5, right, which is my 1/2, times rho v squared, times rho times v squared. And now returning dp in kilopascals, since we're given two reference values in kilopascals, I'll do res is dp divided by 1,000. All right, because pascals to kilopascals, right, I'm going to divide by 1,000. Okay, cool. Now I'm going to test my code out first in the command window. Okay, make sure it works. I can just recall a couple of these. So cast iron, I get 9.1160 kilopascals. Perfect. drawn tubing. I get 3.0864. Perfect. All right, so looks like my answers agree perfectly with the reference values that I'm given, right? And a note on this is, again, right, I needed an error function because I need to numerically solve for f. I did it via an anonymous function only because my expression for f is dependent on my relative roughness and Reynolds number, which already have been defined and exist within my function workspace. And so rather than writing my Colebrook error function as a separate error function in which I have f, re, and relative roughness as inputs, I would then need an anonymous function to pass that additional information to it. So I just did it all at once here by using an anonymous function from the very beginning. Okay. Last thing then, right, in the habit of if this were, say, an exam, would be, say, to create a script, okay, to demonstrate the working of our code. Right, so maybe I have a script to compute pressure drop in kPa for our problem of interest. And then maybe this is, case 1, cast iron with epsilon equal to 0.26, and that's millimeters. And maybe this is case 2, drawn tubing with epsilon equal to 0.0015. Right? So now I just have a script. I'll call it 7.1. Bam. So if I run it, right, I could just click run and exactly reproduce my results. Right? And I see that as relative roughness, increases. Right? We saw that the friction factor increased. Right? And now we see that the pressure drop increases as well. Okay. So cool. All right, so here's my solution for 7.1, right? And if you wanted to, you could generalize this further. You could list a bunch of inputs on here, my diameter, velocity, length, like all of this, right, could be made, those parameters could be made as inputs to generalize it. And then in your script, maybe you define all those parameters for this given problem and then pass them to that function, and that would work as well. Right, so that if you wanted to have some code so that you're ready, no matter what parameters you had, you know it would work. But I guess you would also need to check the Reynolds number to make sure it's turbulent, to make sure that this is valid as well. Right, so it could go either way. So hope that helps. If you have any questions, let me know, and I will get this posted for you.